You unlock this door with the key of imagination. Beyond it is another dimension. A dimension of sound. A dimension of sight. A dimension of mind. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone.
So if you felt lost in the last video, you will feel even worse on this one, because this one I'm gonna push you the limits of how close you can get to things. And so get closer. Closer. A little closer than that. No, closer. Hello? Hi. Imagine getting as close as you can to matter. What will you actually see? Matter is made of these tiny little particles. And most people know that things are made of smaller things, like the cells are made of organelles, and that organelles are made of molecules, and macromolecules are made of tiny little molecules, which are then made of atoms. And those atoms, a lot of people know, are made of things like electrons and nucleons, like protons and neutrons. And then what people don't know, the majority of people, is that those nucleons, protons, and neutrons are made of tinier particles, even called quarks. And that those quarks are essentially energy vibrating in place, trapped, and given ground or an anchor that sticks them to reality or to space. Right. If I lost you already, don't feel bad, because it's about to get worse. But before we talk about matter, let's talk about antimatter. So matter is basically everything you can touch, everything you can see. But everything there is, its opposite could also exist. It goes back to the whole quantum physics thing of that there's the polar opposites that coexist. Now, all universe is made of matter. But if you got the opposite quarks, in other words, everything there is made of the nucleons, atoms, or whatever. But if you get the opposite of those particles, you can put them out there, that's basically the anti-quarks, or the opposite of matter. And I will explain what that is in a second. But basically, for every particle that exists, there's an opposite particle out there. A particle that spins a different way, that has a different flavor, a different strangeness, a different mass, a different spin. Everything is the opposite. And this matter doesn't really exist in our universe. And if it does, it exists separated from all the matter. Because if matter touches antimatter, they annihilate each other. And that's actually what happens inside the sun, you see, because inside the sun, the destruction of protons as the nuclear reactions take place actually produces anti-electrons, which we call positrons. And when those positrons get produced, it actually immediately collides with matter, with an electron, and it annihilates each other in a massive explosion, which releases so much energy that it actually powers the sun. And this has been powering the sun for billions of years. Matter-antimatter collisions. So understand that. Since the beginning of the universe, when the Big Bang took place, more antimatter got destroyed or more matter got created. Whichever way you look at it, the universe has more matter than antimatter, at least as far as we know it. But either way, matter and antimatter are two opposites of each other. So whatever I'm going to teach you about right now, remember, there are particles out there which are the exact opposite of everything I'm going to say. Okay, so matter and antimatter. Now remember from quantum physics that when you study something, you actually affect the thing that you study. And so remember also that everything we're going to be talking about is actually only the beginning of our understanding of how matter actually works, because the fact that we're studying it may actually have affected it. So it might not be the way it actually is. And a lot of this thing is mostly conceptual. And it wasn't until we started doing studies with things like particle accelerators, like the ones you see in the screen, that we actually started observing some of these properties of matter. And though we cannot observe these particles directly, what we actually see is the consequence of the existence of these things that we were going to be talking about. And so we can't really study the particle or the properties of the particles the same way you would study, the temperature of something or the color of something. But you can infer the existence of the particles and of their properties through the way that they act with each other in relationship to each other and so forth. And as soon as we started understanding that there was a lot of smaller things than the things we already knew about, we started finding the need to actually have a way to describe these things the same way we describe things we see in terms of color, texture, and things like that. there was need to actually differentiate between the particles, or the way the particles are acting. And so every single property that was discovered in particle accelerators was then referred to as a quantum characteristic or a quantum property of the particles. And these things include things like isospin, the flavor of the particle, the strangeness, the topness, the charmness, the bottomness, the mass, the spin, the orbital momentum, the total angular momentum, the charge, the parity. And I'm not going to get into detail about what each one of these things are, and whatever is important I'll tell you as I'm discussing the different particles. But remember that scientists have to come up with these arbitrary ways to classify the particles in order to actually differentiate between them. So every particle that is out there is discovered based on what it does and what it creates. And then we have to generate a new way to classify them based on all the different interactions they have with each other. That's where it starts getting really confusing for most people to understand quantum mechanics and quantum particles and things like that. Now, the world of small things is a strange world indeed, and it's a lot different from the world that you live in and imagine. For example, some of the coolest things about quantum physics is that the idea that multiple existences can coexist at the same time, but in different dimensions. Or that particles, or that everything there is actually multiple things all at the same time. And that it's not until you actually observe those things that those things actually take a certain shape or form. In other words, the particles which we're about to discuss, they are different from each other, but they might just actually be all the same thing. And it just might be that when you actually look at them, they're actually acting in a certain way that makes them be a certain particle, but in another way they could also be another particle, and if you look at it from a different angle, it will probably be a different particle. And those crazy ideas are just one example of what quantum physics is all about and why it is so hard to understand the world of small things. And for example, there's evidence that suggests that particles which are separated but used to be together, or particles of the same time, somehow understand each other at a distance from each other. In other words, you're trying to make an experiment to prove a point, and to do that you have to separate the particles, but even as you separate them, and then you treat the one particle one way, the other particle also does the same thing, even though it's separated from it at the speed of light. There should be no way that the particle could be communicating with the other, but somehow they retain some sort of unity, even though they're apart from each other. One vibrates, the other one vibrates as well. It's almost like there's a connection between the particles, something ethereal that actually holds everything together. Almost like everything there is just basically a different manifestation of one thing. And without getting metaphysical on this, because you certainly could, particles are basically manifestations of matter in the universe, and that matter will act differently depending on the context that you looked at it and how you actually look. But at the core, it's all the same thing. It's all energy vibrating and trapped in the same spot. Energy that's been held or anchored together in space-time. So that's what matter actually is. It's a manifestation of energy. And since energy is all one thing, matter is all one thing. And depending on when you look at it, how you look at it, and what else is around it, it will act different. But there are two major components of matter. You have fermions and you have bosons. And these are the basic particles that makes everything there is. Both the stuff that stuff is built of and the stuff that explains why stuff does what it does. So this is what we call in modern physics the standard model of particles. And basically it's a combination of fermions and bosons that makes everything there is. Fermions are basically the constituent parts of matter, what makes matter what it is. It's basically mostly quarks with some leptons thrown around as well. And then the bosons are what gives the matter its properties. So for example, the gluon will give the strong interaction, which is basically the connection that exists between the particles of the nucleus, holding together the nucleus of atoms. The Y bosons and Z bosons mediate the weak interaction. And then you have the photon, which mediates the existence of electromagnetism or electromagnetic forces. And then you also have the theoretical graviton, which mediates the existence of gravity. And finally, the Higgs boson, which actually makes mass be trapped in space-time. It is the ethereal connection that holds together everything that there is and actually makes them have a presence in the universe. That is what we're going to talk about in the next video as we begin by talking about the elementary particles one by one. I'll see you guys then.